My name is Mohammed, a PhD student from USTHB University in Algiers. I'm honored to share my research with you, which is towards self-optimization of publish-subscribe IoT systems using continuous performance monitoring. The goals of our research is to highlight the importance of maintaining a good quality of services in IoT systems and platforms, and faces the impact of the communication layer and object resource limitations on the platform on the performance of IoT systems. Enable continuous performance monitoring for publish-subscribe IoT systems using stochastic Bitnet model. Identify and model key influencing factors on response time. Define a general methodology for improving the performance of an IoT platform continuously. Evaluate the effectiveness of our proposed methodology and performance modeling approach. Let me start by the abstract. Why performance evaluation is important. The number of IoT devices is growing, and experts predict that there will be more than 75 billion connected devices in use by 2025. However, this proliferation of devices brings with it challenges to the use of different technologies for communication, leading to increased complexity in managing and integrating IoT systems. Furthermore, the communication infrastructure supporting IoT operations is often unstable, characterized by frequent disconnections and limited resources such as battery or memory. These factors collectively contribute to the degradation of performance in IoT applications and their mining the user experience and satisfaction. To address this issue, it is imperative to analyze the performance of IoT applications and systems, ensuring the delivery of good quality of services. Now that we have explored the need for performance evaluation in IoT systems, let's move to the world of the IoT. So what exactly is the Internet of Things? The Internet of Things is paradigm that brings together physical objects and the power of intelligence. In this context, intelligence refers to the ability of objects to collect and process data, make decisions, and communicate with other devices or systems. We can break down an IoT system into 4 distinct layers. The first layer, which is collect or actuate layer. At this layer, we are at the level of the connected object. We refer to sensors that enable measurements of the physical environment, such as temperature or humidity, and actuators that can interact with the environment, for example, motors to open or close the door. Some objects may have electronic computing and network capabilities that allow them to connect directly to the network. The second layer is the communication layer, which involves sending data from the local network to the cloud. We primarily focus on the protocols used for transporting data, and 2 models can be distinguished. The publish-subscribe model, which is the publish-subscribe model like MQTT, and the REST model with protocols such as HTTP. The third layer is the data processing layer. In this layer, the data was stored and processed. This is where the IoT platform often comes into play, which is a cloud solution capable of connecting multiple connected objects. The fourth layer is the visualize layer, which involves exposing the services of connected objects through different dedicated applications. For example, a user can communicate with their objects by accessing their data or by accessing their data or by accessing their data or uh, or sending actions to them through a mobile application, for example. In this slide, I want to talk about the impact of communication layer on the performance of IoT systems. In addition to the resource limitations, the communication layer plays a crucial role in the performance of IoT system and the optimal functioning and user satisfaction. Two communication models are usually implemented, the publish-subscribe model and the REST model. The publish-subscribe model, it is a messaging pattern that allows for asynchronous communication between various components in an IoT system. And the REST pattern, in the REST pattern, IoT devices expose their functionality and data through RESTful APIs. Among IoT communication protocols that implement publish-subscribe pattern, the MQTT protocol that has been widely used communication protocol. In the MQTT publish-subscribe protocol, messages are classified into categories. Receivers or subscribers subscribe to a given message category or topic, while senders or publishers publish message to a topic, and subscribers are notified sequentially. Published messages are categorized into classes called topic. So there are three categories of entities: publishers that connect to the broker to publish messages on a specific topic, subscribers that subscribe to a topic, and a broker that controls the distribution of information by receiving all messages from publishers, filtering them, deciding who is interested in it, and then sending the message to all interested subscribed clients. The research or performance analysis and optimization of Internet of Things system has gained significant traction in recent years. When studying the proposals, we noticed that some of them used query network or process algebra, which is formalism, not able to model all system properties. Others base their performance analysis on benchmarking or testing simulation tools that are cost time sometimes. In addition, if an IoT platform needs to derive performances periodically to check quality of its service, or there is a need to predict performances of a system before its operation, no efficient approach is recommended for carrying out a performance prediction or analysis of a whole IoT platform. So we introduced then in our paper a general performance modeling and analysis method for IoT systems. We follow an approach, by example, where we study performance analysis of the MQTT protocol. In this slide, I will present my monitoring process. At the core of our research lies a novel three-step methodology that enables continuous performance monitoring and self-optimization of publish-subscribe IoT system. The first step is to monitor and capture the current configuration of a workload of the target IoT systems. The second step, we construct a stochastic Petri-net model configured with parameters captured in the previous monitoring phase. As described in the paper, SPNs are well-suited for modeling the concurrent and probabilistic behavior inherent to IoT. Using this SPN model, we can compute critical performance metrics like response time for publication requests from publishers and notification deliveries to subscribers, which brings us to the third and final step. Is if our SPN analysis indicates that the system's performance has degraded below thresholds, we apply predefined optimization actions. These actions involve modifying one or more of the influencing factors, such as broker memory allocation, or, for example, network buffering, or quality of services levels. It is important to note that this three steps process is iterative and cyclical in nature. We continuously loop through monitoring, modeling, and optimization, ensuring the IoT system's performance remains reliability and high despite functional fluctuation in its operation environment. We followed an approach, by example, to define our modeling approach. For this aim, we study an MQTT publish-subscribe based IoT platform to effectively model the publish-subscribe platform. We adopt a modular approach. Each component, including the client connection, for example, publication, notification, is modeled separately as submodels. We start by the first submodels. The submodels in the left represent client's behavior, which can be publishers or subscribers. This submodel focuses on the client connection and disconnection process. It models a publisher or subscriber through a place containing client instances, as it's making in order for a client to publish an event or subscribe to a topic, it must first establish a connection with the broker server. This connection process is captured by the connect transition within the submodel. Once a client initiates a connection request, the broker represented by the broker place checks if the request can be accepted according to its available resources. The acceptance of the connection request is modeled by the accept transition, which takes into account the broker capacity place, modeling the maximum number of clients that can be connected simultaneously to the broker. If the connection request is accepted, the client token moves from the publisher to subscriber place to a new place represented a connected client. The submodel on the right captures specifically subscription and unsubscription process for connected subscribers. At the core of this submodel is a dedicated place named topics that represent possible topics to which subscriber can subscribe. The subscription process is initiated by the subscribe transition. This transition establishes the association between subscriber and the desired topic, enabling them to receive related messages. Importantly, subscribers also have the flexibility to unsubscribe from topics via the unsubscribe transition when they no longer wish to receive associated messages. The third submodels on the left is the publication submodels. which represent the publication process for connected publishers. Mainly, we have the publish transition, which is triggered when a connected publisher has an event or message to publish. The event or message to be published are represented by tokens in the event to publish place. The submodel on the right is the subscriber notification submodel. When a message is published for a specific topic, the broker is responsible for notifying subscribers who have subscribed to the same topic. This notification process, represented by notify transition, consists of delivering the published message to interested subscribers. Once the submodels were developed, we merged communicating transitions for interacting each submodel with other to obtain the overall SPN model representing the entire IoT publish subscribe platform. Each submodel captures specific system behavior, and their composition enables modeling the full system. There are several factors that may affect IoT systems performances, and in particular response time. We give below main factors: broker memory, network buffering, and quality of service level. I will show one of our experiments, which is response time compared to the quality of services and the notified response time. We conducted this experiment to show efficiency of quality of service modification action, which can be applied to an IoT system whenever performance are degraded. Hence, we show how performance may be degraded when quality of service processing rate increase. For this purpose, we vary in our SPN model the publish quality of service processing transition rate and compute the broker response time needed for accepting and processing a publication for publishers, and the response time required for notifying a subscriber. In the slide, we observe how the publish quality of service processing transition rate affected publication response time as well as subscribers notification response time by reducing quality of service in a broker. By reducing quality of services level in a broker, we improve processing times. The higher our processing rates, the more rapid publication and notification can be processed, resulting in reduced response times for both publishers and subscribers. In this paper, we have presented a performance monitoring methodology to enable self-optimization of publish-subscribe IoT system. Our approach leverages stochastic Bitternet modeling and analysis to predict performance metrics and identify influencing factors on response time. A key advantage of our methodology is the modular modeling approach based on submodels. We develop submodels representing the different components and behaviors of the MQTT publish subscribe IoT platform, including client connection, subscription, publication, and notification. The submodels were then interconnected to form the overall SPN modeling of the system by composing the reusable submodels. We called accurately capture the dynamic and performances of the complete IoT platform. We conducted experiments to demonstrate how our SPN model can be used to monitor factors like quality of service, level, network buffering, and broker memory utilization. The results showed that by detecting degraded performance and modifying of influencing factors, and our approach can significantly improve response time.